Hi, welcome to the 23rd session on measure theory. This is the sixth session on Lebesgue integral. Today we will have two parts. The first part is some small but useful results about integrable functions. Quite often they are very used, and just like that they are used, but in the beginning one should get a complete idea and the proof. And second thing is we will see how to extend whatever we did about measurability and integrability, okay, of real valued function to complex valued functions. Now luckily in complex valued function we don't allow plus infinity at all. Okay, it takes values only in the complex number system. Okay, in some sense that's easy also. Okay, so let us first prove some other small little useful results about integrable functions. So the first thing, okay, so it's a miscellaneous result. Okay, on integral functions. Okay, so we are fixing as usual a measure space. Okay, the first thing is almost everything. Look at the pun. Almost everything depends upon almost everywhere notion. Okay, the first thing is let's assume that f and g from x to re measurable, and assume f equal to g almost everywhere, and f is integrable. Then what you want to claim is g is also integrable. Okay, notice that if the measure space is the Lebesgue measure space, okay, if f is measurable and integrable, f equal to g almost everywhere, then g is automatically measurable. I don't assume measurability. Or in any complete measure space also the same thing. If x b mu is complete and f is measurable and integrable and g equal to f almost everywhere implies g is measurable automatically. Okay, right. So the proof is easy. So what we do is look at the set D. Okay, so that f is not equal to g. That is set of all x in x, so that fx is not equal to gx. Okay, and since f equal to g almost everywhere, the points at which the d differs, this is measurable, d is measurable, and measure of d is 0. Okay, f equal to g almost everywhere implies this. It's actually if and only if. Right, now what we want to do is we split my x into two sets, E union D, where E is naturally x minus D. Then these are all measurable, these are partition. Therefore I know integral of f, okay, right? So you can even say modulus, but let us see, let us try to understand this. Since I want to say f is integrable, that g is integrable, that means I have to show mod g over x d mu is finite. So let us start with mod a, this. Okay, this I know is finite. Okay, but this is equal to non-negative function, therefore this is, we had already seen this, mod f d mu over d, right? But notice that mu of d is 0. Therefore for any measurable function phi, okay, integral of phi d mu will be 0. Okay, so I can split phi as phi plus and phi minus, then I will show that integral of phi plus is 0 and integral of phi minus is also 0. Therefore you can as well assume phi is non-negative, right? But that is very easy because you start with any simple function which is less than or equal to phi and phi, okay, then what happens? Integral of s over d by the, and suppose this is the standard representation ci, indicator function of ai, then integral of s over d, we have seen already is ci mu of a intersection d, but this is 0. Therefore, this is 0. Therefore, this is 0 for every such as, therefore, phi is 0. You understand? Okay. Therefore, one of the things which you proved was this. Okay. What did you prove? If f is measurable and d is a measurable set such that mu of d is 0, that implies integral of f d mu is 0. Okay. Pause. Review. Proceed. There are a lot of some small things. Okay. Don't worry about trying to remember. Go through the proof and assimilate the proof. Then you will be able to recreate the proof on your own later. Okay, you can simply use it. If anybody challenges you, you should be able to give a proof. Okay, now let's come back. So my f is integrable. Therefore, we said mod f over x is integral of mod f over e d mu plus integral of mod f d mu over d. But this is 0, right? But notice, for the same reason, let's look at mod g of d mu. This over x is going to be integral of mod g d mu over e plus integral of mod g over d mu, that is 0. But these two are equal because mod f equal to mod g on e. You understand? Yeah, there, and this is finite, right? Because mod this is finite, therefore this is finite, that means this is finite, therefore this is finite. So this implies g is in L1. Okay, P R. And second result is monotonicity. Suppose f and g are in L1, okay, and f is less than or equal to g, right? Then I want to say integral of f is less than or equal to integral of g. Of course, this is with respect to mu. Okay. This again is easy. You will see. We have proved it for non-negative functions, right? Let's look at g minus f. Then this is greater than or equal to 0, right? Therefore, and this is measurable, and therefore integral of g minus f d mu over x is greater than or equal to 0. That's correct. But remember, f and g are integrable. Therefore, by the linearity of the integral, this object is nothing other than integral of g over x minus integral of f over d mu. Right? That is greater than or equal to 0. That implies integral of g d mu is greater than or equal to integral of f d mu over x. So here. Again, almost everywhere version is also true. Assuming f and g are measurable, f is less than or equal to g almost everywhere. The same proof will show this also, right? Check almost everywhere version. Okay, the only thing is you have to assume f and g are measurable. In the case of complete measure space, if you assume that f is integrable, okay, and you will assume f and g measurable. F and g measurable, and f is less than or equal to g, then this. That is f is less than or equal to g almost everywhere. So you can split the integral into two parts as usual. Okay, just check it out. Okay. So the third thing we want to do is, suppose my f is in L1. Okay. Do you remember I said I will use L1 only, but I had been using today ordinary L1, but that does not matter. So it means only integrable. Okay. Right? Then I want to say f is finite almost everywhere. Okay. Since f is integrable, if only mod f is integrable. Therefore, if I show, yeah, this means f is mod f is finite almost everywhere, right? Okay. So how do I do that? Okay. So let us look at this. What does it mean? This means what is that I have to prove? Let E be the set of points x in x such that mod f at x, that is mod of fx, equal to infinity. Then we want to say, notice that this will be measurable because f is measurable, therefore mod f is measurable, and therefore equal to infinity, that is measurable. Therefore this is a measurable set. So when I want to say this is finite almost everywhere, this means hypothesis implies mu of e is 0. Okay, clear? Okay. Now the result is easy, the same way. Therefore integral mod f, okay, oh, I want to prove what is it? Finite almost everywhere, right? Okay, right. Okay, suppose false, right? Then mu of e is positive. So we want to, sorry, no, this is not hypothesis, we want to prove. F is integrable, then I want to prove this is finite, sorry, not hypothesis, conclusion to prove. I'm sorry, okay, so forget this. So I want to prove f is finite almost everywhere, that means mod f is finite almost everywhere, that means the set E is measurable, mu of E is 0, that's all I have to prove. Suppose false, that means mu of E is positive, right? Correct? Okay, now the integral of mod f over x, I can split it into two things. Integral of mod f over x minus e plus integral of mod f over e. Okay, but notice that this fellow is greater than or equal to infinity times mu of e. Since mu of e is positive, this is equal to infinity, right? But our assumption is this is finite. So this is a contradiction. Hence, mu of e is 0. Okay. The last one, this is the third, right? The last one is very often used. Okay, I do not, if you have gone through my first 3 lectures, you have seen that if CIs are non-negative for an indexing set, then we define summation CI. Okay, we define the meaning of this sum. Okay, and then we said this is finite if and only if CI is non-zero, okay, only for countably many. Okay, this we saw. If you don't recall, forget it. Okay, so its analog is what we want to prove. Suppose my f is in L1, then I want to define what is meant by the support of f. We will denote it by the shortened notation. This by definition is set of x in capital X so that mod of x is not 0. Fx is not 0, which is same as saying in our case mod fx is not 0. Usually the correct definitions, fx is not equal to. Okay, but in our case it turns out to be same as mod fx is not equal to 0. Okay, correct? So we want to say this, okay, is a set of sigma finite measure. I will explain what it means. If you are in a measure space X be mu, a subset E in S in B is of sigma finite measure, is sigma finite if there exists En and B so that mu of En is finite for all n and E is union of En. For example, if you look at R with the standard measure space M, then R is itself is sigma finite. Why? Because R is disjoint union of minus n to n. These are all of finite measure, right? Remember sigma means sigma additive, etc. You remember sigma countable, something with countability. So it's countably finite. That means it's a union of countable union of sets of finite measure. Okay. That is. So therefore E is sigma finite. This means it is the union of countably many sets of finite measure. When I say sets of finite measure, that means these sets are measurable sets automatically. Okay, that is again easy because let us look at my En. Okay, set of x in capital X, so that mod f x. Okay, this is greater than 1 by n. Right? Yeah. Notice that my En's are all contained in E. What is E? E is the, okay, I have not defined. E is the support. E, which is the support of F, which is set of all x in capital X, that mod f x is not equal to 0. So by Archimedean property, this 0, this is mod f x. Okay, therefore there is 1 by n. Yeah. So this shows that En's actually are increasing. Okay, but union En is x, and En, sorry, not x, E. En increases to E. Right? Because give me any x here, as I said, mod f x is positive by Archimedean property, there is a 1 by n, which is strictly less than mod f x. Therefore, that x belongs to U. Right? Okay. So, yeah. Now, and is this clear to you? Right. Now, what do I know? My E is a union that I claim mu of n is finite. Claim for each n. Okay. If false, there is an m so that mu of m is infinite. Right? Now let us look at this. Integral of mod f over x is greater than or equal to integral of mod f over em, because mod f is greater than or equal to IEM times integrated function of this into mod f, right? But on this greater than or equal to 1 by m times measure of em, which is infinite, therefore this is infinity. But this is finite because my function f is integrable. Okay, so these, as far as I remember, these are the small results which will be used many times in any kind of measure theoretic course. So you please go through them. All, as you can see, all are very, very easy. Sometimes they are not even mentioned, but in the course of proof later, we will keep using it freely. Okay, but it's better to check it in the beginning, right? So that more or less I think it completes whatever I wanted to talk about integrable functions. Now the next task is to extend the notion of measurability and integrability to functions that take values in complex numbers. And life is very simple there. Okay? What is the obvious way? You write f. Suppose f is complex valued, you write f equal to u plus ib in the complex analysis notation, where u is the real part of f, v is the imaginary part of f. Then I am going to say f is measurable. Definition. F is measurable if and only if u and v are measurable. Okay, I can give an independent definition, but let's not worry about it. Okay, this is the easiest and this is the most practical definition, and it's a perfect definition, right? You understand that? Isn't it life easy? Yeah, so let us get started. So let F be from X to C, we say is measurable if real part of F and imaginary part of F are measurable. Remember, real part of F at X is real part of the complex number F of X. Right? The standard notation in complex analysis, you write F equal to U plus IV, then F is measurable if only if U and V are measurable. That is our definition. This is our definition. Right? And therefore, the algebra of measurable functions is easy. Complex valued measurable functions. Okay. Right? Because if F is U plus IV and G is U1 plus IV1, okay, then F plus G will be U plus U1 plus I times V plus V1, and these are measurable, etc. etc. Okay, it's a boringly easy, so I don't want to spend time on that. Okay. So next, what do you want to do? How do I define integral then? Suppose F from X to C is measurable. Okay, I want to talk about integral of F d mu over X. How to define? So based on this earlier trick of measurability, the obvious definition will be look at integral of U d mu over X plus, remember it has to be a complex number, therefore I should write I of integral V d mu. Right? But then this must be a complex number because okay, this must be a complex number. That means this must also be in R. This must also be in R. Then only I will have sense. So what we say therefore is, right? We say F is integrable if mod F is integrable. Okay, where what F is? F is complex valued function. Right? Then I want to claim F is integral if and only if U and V are integrable. Okay. This is an observation. This is our definition. Okay. Why this is true? Notice that for any complex number z equal to x plus iy, mod x is less than equal to mod z, and mod y is also less than equal to mod z. Therefore, mod u is less than equal to mod f, right? And since f is integrable, suppose f is integrable, that means mod f is integrable, right? Therefore, this is also integrable. And similarly, mod v is integrable. Therefore, f integrable implies u and v are integrable. Okay. The next thing, again the same thing. For any complex number, notice that mod z is less than equal to mod x plus mod y. Yeah, because take the square, then you know that this is a mod x squared plus mod y squared, whereas it will be mod x squared into mod y squared plus, okay, an extra term आ गया, 2 times mod x into mod y, which is non-negative, right? Therefore, mod f is less than equal to mod u plus mod v, right? Therefore, if mod u and v are integrable, let u and v be integrable, then mod, observe this, mod u is, right? And therefore, mod u plus mod v is also integrable, right? And a function is less than equal to integral function. By the one of the earlier observations of the last session, mod f is integrable. Remember, in the last session we proved this. F g measurable, f integrable, and mod g is less than equal to f, assuming f is non-negative. Okay, then g is integrable. Okay, that's what I'm using. Okay, this is my f, this is my g, this is integrable, therefore this is integrable. Right? That means, therefore, if I define integral of f d mu to be integral of u d mu plus I integral of v d mu, this is a real number, this is a real number. So my assumption is, assume f is integrable. And define integral. You see that? So again notice that we define what is meant by integrable first, then only we define the integral. Okay, we apply the notion of integral only to the integrable function. Okay, and how did you define integral function? That we reduce to the non-negative function, namely f is integrable if mod f is integrable. Okay, please keep that in mind. Right? So what are the things I want to do? So now let x1 x b mu c be the set of c valued integrable functions on the measure space x b mu. Hereafter we will simply write it if necessary except or if this one. Okay. Now I want to show this is a vector space. Of course, naturally over C. And the map f from here going to f d mu is a linear C linear map. Linear over complex numbers. Okay, this is what we want to prove. Okay, again these are all very easy. Okay, I don't want to look at addition etc. So I only talk about, it's very easy to see integral of f g d mu is integral of f d mu plus integral of g d mu, because if I write f equal to u1 plus iv1 and g equal to u2 plus iv2, then f plus g will be u1 plus u2 plus I times v1 plus v2. Notice that these are all integrable now. Therefore, when I take integral, this will be integral, this will be integral of u1 plus integral of u2. This will be I times integral of v1 plus v2, but that will be integral of v1 plus integral of v2. Because of integrable, these are all integrable. That's why I can do that. Okay. Then I combine them together, u1 plus I times integral v1, this and this, this and this, and similarly integral u2 plus I times integral of v2. But that is integral f plus integral g. These are all boring. Let's okay, easy, just to make sure that you understand. The next thing to prove linearity, C linear, it's enough if we prove at I, that is integral of IF is I times integral of f. Because I know if A is real, then integral of AF will be A times integral of f. Why? That is because if A is real and f is u plus iv, then the real part of f will be au plus I times ab. Right? Therefore, integral of AF will be integral of au plus I times integral of ab. But integral over for real integrable functions is a linear map. Therefore, this is a times integral of u plus I times a times integral of v. Right? Therefore, a times integral of u plus I times integral of v. That is a times integral of u. Okay? So, we need only to prove this. But that is also easy, Because if f is u plus iv, what is I times f? That is iu minus b, that is minus b plus iu. Therefore, integral of if by definition, this by definition is integral of minus b plus I times integral of u. But remember, u and b are all integrable, therefore this fellow is nothing other than minus of integral b plus I times integral of u. Right? Okay. But then, let us look at I times integral of f. This by definition is I times integral of u plus I times integral of v. Therefore, it is I times integral of u plus I times I is minus 1. Right? Minus integral of v. So, these two are equal. Therefore, we have proved the map L1 of xc, the set of complex valued integrable functions on the measure space X, is a complex vector space, and the map F going to integral f d mu is complex linear. Right. And those of you who have been watching my analysis all the time, you will know that analysis means you have to estimate. Very rarely we can compute the integrals explicitly. So we need to only learn to estimate integral. So what is the most important? Estimate for integral. That is the one we are going to do. Okay. Once I do that, I will stop there. Okay. Yeah. So let us do it. So this is the fundamental basic estimate. So let f be in L1xc, then modulus of the integral f d mu is less than or equal to integral modulus f d mu. Okay, this is the basic estimate. Yeah? Is the statement clear? Right. How do I prove that? The basic thing is easy. We are going to make use of the fact, okay, the integral as a map is complex linear. Okay, that is the basic thing we want to do. And second thing is monotonicity among the real integrals. That is, f is less than or equal to g for real valued functions, then integral f is less than or equal to integral g. So we are going to make use of these things. Now suppose alpha is any complex number. First notice that if integral f d mu is 0, nothing to prove. Prove because this will be greater than or equal to 0 and this will be 0, right? So assume integral f d mu is not 0, right? And call this number as alpha, right? Since alpha is not 0, then I can write alpha as mod of alpha times e power I theta. You understand this? So what I want to estimate is this is nothing other than mod alpha. I want an estimate for mod alpha is less than or equal to integral mod f d mu. This is what we want to prove. Right? So how do I get mod alpha from alpha? That is, I can write, when I want to get mod alpha, multiply by e power minus I theta times alpha, then I get mod alpha. You understand that? Right? So this fellow is e power minus I theta times integral f d mu. Okay, forget it. Right? Do you follow this? But notice that this is by complex linearity is integral e power minus I theta times f d mu. Remember, if f is integrable, e power minus I theta f is also integrable and complex linearity works, therefore this goes down. Now notice that this is a real number, in fact non-negative, right? This is positive number, this is a real. So by the definition of integrability, this fellow is nothing other than the real part of e power minus I theta f d mu. Because this is a real, right? Yeah, but notice that this is a number is a real number. This real number is less than or equal to e power minus I theta f. This real number at x, each x is less than or equal to modulus of e power minus I theta f. For each x, if you want, let me write each x, right? But this fellow is just mod f x. Do you follow that? Therefore, by monotonicity, okay, this fellow is less than or equal to integral mod f d. Is the proof okay? Yeah? Pause, review, proceed. It's a very slick proof. Okay. So what did we do? We took this integral to be non-zero. Then call it alpha. Then mod alpha is given. If alpha is equal to mod alpha and e power I theta, then mod alpha is e power minus e theta into alpha. So I write it. Now I use the linearity here of the integral. So e power minus I theta slips in under the integral sign. Okay. But notice that this, okay, because this is non-negative, this is real. And this is a complex valued function to start with, right? Therefore, what does it mean? If I write it as, okay, real part of this object plus I times imaginary part of this object, okay, this is 0. You understand that? Therefore, this equal to this part. But for this real number, okay, now I can use monotonicity. Since it's a real number, okay, this fellow will be less than or equal to modulus of this number, but that is less than or equal to mod f x. Okay, so that is the proof. Go through. So did you like the proof? Yeah. For example, in particular, suppose f is only real valued, integrable, then also instead of u power I theta, integral f d mu, either it has assume it's non-zero, either it is positive or negative. Therefore, you multiply by epsilon, where epsilon is plus 1 or minus 1, so that epsilon times the integral becomes positive. Are you following? So what I mean is, even for a real valued function, the proof works. Right? Okay, please understand. Let me just check the time. There is still some more time. So let us try to apply this result somewhere. Okay? There are few results we can do that. I will just do one easy result just to show the power. So an application. Today I have not used a blue color, right? Let me use it. Suppose f1s are measurable. Okay, maybe R or extended real. Okay, as I said, the above proof works are for extended real also. Okay, if f is real, takes values in Re, okay, then define an integral f d mu is non-zero. Remember, it's integrable, therefore it's finite, right? Therefore, either it is positive or negative. Therefore, modulus of this integral f d mu equal to epsilon times integral f d mu, where epsilon is 1 if this is positive, equal to minus 1 if this is negative, right? Then the same proof, instead of u power minus theta, I have epsilon, push epsilon inside the integral, argue. Okay, so the point I want to say is, even if it is extended real valued function, the basic fundamental inequality is true. Okay, that is what I want to say. Okay, right? Now suppose my fn's are integrable, and let us assume fn converges uniformly on x to a function f. Then we know f is measurable. Right? What I want to claim is two things. I want to say f is integrable and integral fn converges to integral f. Okay. This is not going to be exactly correct. I may have to put an extra assumption. Okay. Let us just play along. Okay. Let us see. We try to do that. Recall, how did you prove in the case of Riemann integral functions. Assume that f from a, b to r, assume they are all even continuous, then f1 converges to f, okay, uniformly on AB, right? Then what I want to show is, then f will be continuous, therefore f is will be Riemann integrable, right? Now therefore integral f makes sense. A to b, fx dx makes sense. So what we want to show is integral fn a to b, fn of x dx converges to integral a to b, f of x dx. Okay, how did we prove that? We try to estimate integral fn of x dx, a to b minus integral a to b, f of x dx. But linearity will tell me it is fn of x minus f of x dx between a and b modulus, but that will be less than or equal to modulus here, right? But since this is uniform, okay, given epsilon positive, there is f1 converges to f uniformly. Therefore, given epsilon positive, there exists an n, so that for all n greater than or equal to capital N, and for all x in a, b, modulus fn x minus fx is less than epsilon, right? Therefore, if n is greater than or equal, therefore, modulus of integral fn dx a to b minus a to b fx dx is less than or equal to integral a to b modulus f1 x minus fx dx. If n is greater than or equal to capital N, this is less than or equal to epsilon. Therefore, it's epsilon to b minus a. Right? So that proves the convergence. Okay, this implies integral f1 a to b x dx converges to integral a to b fx dx. Okay. Now I can try to mimic the same proof here. So let us do that. So I have x fn of x minus integral x f of x dx. Okay. First, why this should be measurable? Sorry, why f is integrable? Okay. In the earlier case, you saw that fn's are continuous, and therefore the fn converges to f uniformly. Therefore, it will be continuous. Therefore, it's Riemann integrable. Here, I don't have that. Yeah, I only know f is measurable. But why is f is integrable? So that means I have to show mod fx, okay, d mu is finite, right? The only thing I know is the following, okay, mod fx, the only estimate I have is less than or equal to mod fn of x minus fx plus fx. Sorry, I'll write it here. Less than or equal to mod fx minus fnx plus fnx. Right? This I know is less than epsilon. Okay. For all n greater than or equal to n, assume the same notation. Given epsilon positive, by uniform convergence, implies there exists n, so that for all n greater than or equal to capital N, mod f of x minus fnx will be less than epsilon. Right? Therefore, mod f of x I can write is less than or equal to epsilon times mod fnx for all n greater than or equal to n, in particular for capital N. Right? Therefore, when I want to integrate this mod f of x over x, this is less than or equal to integral of epsilon plus integral of mod fnx. My fn's are all integrable, therefore this will be finite. But this will be epsilon times mu of x. Okay, this has to be finite, that means mu of x has to be finite. So I have to put an extra assumption. So we add an extra assumption. What is that? Mu of x is finite. Therefore, what is the result? I have x b mu a finite measure space, that is mu of x is finite. Fn's are all in L1, Fn converges to F uniformly, then yeah, F is of course measurable and F is integrable, and integral Fn converges to integral F. Okay, this is the statement. So we had already seen F is measurable. Now we proved under this extra assumption F is integrable. And this proof is exactly the same. No. F and du mu minus F du mu. Okay. Now since these are integrable, linearity of the integral will tell me this is integral F1 minus F du mu. Therefore, modulus of this fellow by basic inequality will be less than or equal to this. Right? If n is greater than or equal to capital N, this will be less than or equal to epsilon. Therefore, this is epsilon to mu of x. So the proof is exactly the same as the earlier one. Right? So, in the case of Lebesgue integral also, uniform convergence of a sequence of measurable function of integrable functions. Okay, the limit function will also be integrable provided, okay, the space on which you are integrating is a finite measure. That's only as then the proof is okay. Yeah. So I hope you enjoyed all these things, right? And in the next session, we are going to prove the third most important convergence theorem. That one, okay. So far, the earlier two things we needed function to be non-negative. This function, the third one which we are going to prove, dominated convergence theorem, will not require Fn to be non-negative. Don't worry, we will explain the statement and give a proof in the next session. Okay, take care, stay safe, we will meet again.